Welcome back to another riveting episode of Who Wants to Be a Mathematician. I'm your host, Mr. Hill, coming at you with 2.4c, Limits and Continuity Part 2. So in this episode, we're going to be talking about finding whether a function is continuous or discontinuous and how we're going to do that. So we're going to start off with talking about the definition of continuity. So there's three parts of this. The first part, the second part, and the third part all talk about if we have some sort of continuous line. Doesn't matter how where it is, what's going on, doesn't matter. As long as it's a continuous line, then we can take any point and figure out if it's continuous. So the first part is if we have a continuous line, if we take this point and we come from the left and right hand side of it, the limit is going to be the same. So we're going to say the limit as x approaches some, doesn't matter what number, any number, because if the line's continuous, every single number we'll pick will work. So the limit as x approaches c of our function is going to exist. And we're going to call that L. We also know that if we have any point on our line, let's say our variable c, just any number, that the function does exist at that value. Because if it didn't exist, we would have a great big hole. We don't want holes, we want it to be continuous. So we're going to say that the function at c exists. And if the first part is true and the second part true, then we're going to say that the limit as x approaches c of our function is going to be equal to the value at that point. So if we just have a random line and we're going to pick one point on it, and we figure out that the left hand side and the right hand side are all approaching this one y value, well, that's going to be the same as if we take our function at that point. So the limit is going to indeed be that value. So we could say that's even L right there. So that's the definition. So now let's do some examples and talk about what is going on. So if I have a function, let's say x squared plus 1. Well, for something to be continuous, we have to have a continuous graph. That's to say that if we were to plot this, we know that from our shifts from pre-calc that we're up 1 and we're a parabola. Well, is there any discontinuity here? No. So it must be continuous. So we just know that a parabola is continuous. And how else would we know? Well, if it was discontinuous, then there could be a vertical asymptote, there could be a jump, or there could be a hole. And none of those are the case here. So it's just continuous. Now, if we have a little bit more of a tricky function, let's say a piecewise function that's 2x minus 1 and x, when x is less than 1 and x is also greater or equal to 1, well, we know that we have to check the limits. And why we know that is because we have a greater than or equals to and a less than. So if we know that, then we have to check our left hand side. We also have to check our right hand side. And we know it's the left hand side because it's less than over here. And we know it's right hand side because it's greater than over here. So the first thing we always try to do with limits is to plug in. So we're going to plug in the left hand side and we're going to get 2 times 1 minus 1, which is equal to 1. And on the right hand side we plug in and we get 1. So right now we have the left hand side is equal to the right hand side. So part 1, we know that the limit as x approaches 1, because that's our number, our awesome number here, that's where this number comes in, of our function is equal to 1, because our left hand side and our right hand side agree and they are 1. So the second part says that our f of c value, and our c value is going to be 1 because that's our blue friend there, and we're going to have to plug that in. Well, the only way that we know what f of 1 is if it's equal to. So this second equation here has an equal to sign. That's what the greater than equal to is, and we're going to plug that into our x value, and we're going to get 1 out. So we know that the limit as x approaches 1 of our function is equal to 1, which is equal to our f of c. So we have shown that this is continuous. We used part 1, we used part 2, and therefore part 3 was true. So if we have a function that has absolute values on top and the same thing in the denominator, we know that the graph is going to look like this. And if the graph looks like that, what type of thing do we have? Well, we have a jump. So there's going to be a couple ways that I'm going to let you kind of shortcut the definition. Is the first way is going to be what we did up above with our parabola. We knew that the parabola is continuous, so we just said it was continuous. We know it's continuous. And the second way is that if we have these absolute value functions, we know they have a jump, so we can just say they jump. And that means it is discontinuous. Continuous. So we know there's a jump, so it's discontinuous. Well, if we have this type of function, another piecewise, if x is less than 1 is less than 2, and we have x cubed, is that x squared or x cubed? That's x cubed. Alright. Is 0 is less than x, which is less than or equal to 1. Well, if we have less than or equal to signs, we know that we're dealing with left and right hand limits. So I'm going to pick the number that's the same for both, and that's my 1 value. And I'm going to pick the right hand side of 1. Well, the right hand side is going to be the greater hand side, so that's this one. Now my left hand side is going to be the less than value, so that's this one. So what we try to do, we plug in. So if we plug in 1 on top, we get 1. If we plug in 1 on bottom, we get 1. So we know, since our left and right agree, that the limit as x approaches 1 of our function is equal to 1. So this is part 1. Our limit exists. Let's check out part 2 of our definition. So we need to know that this exists and it's equal to our 1 value. So f of 1, we look at our equal right there, boom, and we know that the limit as x approaches c of our function is equal to our point. And by the definition of continuity, that's all we need. So now we know it's continuous. So I want you to try E and F by yourself. Pause the video, give it a try, see if you can figure out if it's continuous or discontinuous, and we will go from there. So pause me and then jump right back in. Alright, so we're going to look at this, and I don't like the bottom being unperfect, so I'm going to factor that. I don't like it being in the perfect square form. The difference of two squares, we have x squared minus 1 squared, different of two squares, so we can break it up. And I notice immediately that we have a hole. So there's a hole at x is equal to 1, and I notice from the second piece that I have a VA at x is equal to negative 1. So if I have a hole in a vertical asymptote, that means I have an infinite discontinuity here, infinite, and I have a hole, so therefore this function is discontinuous. And you should have tried f already, but if you haven't, then pause me and go on to that one. So we have f of x is equal to x squared minus 1 all over x cubed plus x squared minus 2x. So pause me, give this one a try, and come on back. So I know the numerator is the difference between two squares. I can pull an x out of my denominator, get x squared plus x minus 2. And I know my numerator stays the same. Whoop. But my denominator can turn into x plus 2 and x minus 1. So immediately I notice I have a hole. So I have a hole at x is equal to 1. I have a VA at x is equal to negative 2 and 0. So if I have that, then I have an infinite discontinuity. So you have to say both of them. You have to say you have a whole and that you have a VA. So you have to state what type of discontinuities you have. So it turns out that neither of those are continuous. So last but not least, we're going to move on to creating functions so that they are continuous. So I have this function cx minus 2 when x is less than 3, and x when x is greater than or equal to 3. Well, for something to be continuous, we know that my left-hand side has to equal my right-hand side. If back from our picture from before, if we remember this, my left-hand side, if I'm continuous at any point, those have to be equal. So let's start off with that. So my left-hand side has to equal my right-hand side. So if I were to plug in 3, I would get c times 3 minus 2. And down here I would get 3. So my left-hand side has to equal my right-hand side. So what I'm going to do, I'm going to bring that over here. 3c minus 2 is equal to 3. All I did was take this side and that side, set it equal to each other. We have a simple equation. We get 3c is equal to 5. c is equal to 5/3. So all we have to do is just find that number so that when we plug it back in, we get continuity. And we start off by saying left-hand side is equal to the right-hand side, because we know that from our awesome picture over here. So simple algebra. But of course, simple algebra gets a little more complicated as you add more equations into. So let's suppose that we have 2x minus 1 when x is less than or equal to 1. And we also have cx squared minus d and x when we're between 2 and 1, but also when we're greater than or equal to 2. So same thing as before. I'm going to find my left-hand side and right-hand side, but there's a trick because now I have two numbers. I have my 2 and I also have my 1. So I need to create two different left-hand sides. So my left-hand side and my right-hand side, you could say of 1 here if you wanted to. So the left-hand side of 1 is going to be when it's less than 1, which is my first function. So I plug in 1, I get out 1, because I have 2x minus 1, and if x is 1, then we just get 1 out. Ooh, that's kind of messy. But my right-hand side is going to be my second function, and when I plug in 1 for that, I'm going to get c minus d. Now that's only half of our worries, so we're going to look at the left-hand side of 2 and the right-hand side of 2. So the left-hand side is when we're less than 2, and that's here. So we're going to plug in 2, and we're going to get 4 times c minus d, and we're going to plug in 2 at the bottom and get 2. So now, if you notice, I have two different equations. I have 1 is equal to c minus d, but I also have 2 is equal to 4c minus d. Well, now we just have a system of equation, and I'm just going to, I'll solve for c on this side, and then I'll plug c in to my blue equation and get 1 plus d. And then, so now I have 4 is equal to 4 plus 4d minus d. 2 is equal to 4 plus 3d. Subtract, and negative 2 is equal to 3d. And I get d is equal to negative 2/3. And of course, the last thing I do is plug back in. So I have 1 is equal to c plus 2/3. So c is going to be 1/3. So I have found my two values that will make that equation true. So now what I want you to do is move on to the next one, see if you can just solve this one. We have f of x is equal to the quantity 2x minus 1, x less than or equal to 2, and cx squared when x is greater than 2. So pause my video, see if you can solve this one, and we'll go on from there. Welcome back. We have our left-hand side here, we have our right-hand side here. Simple enough. We're going to plug in and we're going to get 4 minus 1, which is 4 minus 1 is 3. We're going to plug in 2 here and we're going to get c times 4. So I have 4c is equal to 3, c is equal to 3/4, and I have found my value. Simple enough. So when we meet up next, we'll talk about the intermediate value theorem and how we go from there.